All right, so we're starting with example 2 today. Yesterday in example 1, we started with $100, and then we had something increased by 30% every single year. We looked at the pattern, and from the pattern we were able to discern that the equation, the formula, if you will, that gave us the amount A at any given time t was equal to 100, the initial amount, times 1.3, the base, raised to the tth power. Okay, so what we're going to try and do on example 2 is, without showing all the pattern, but based upon our conclusion up here, we're going to see if we can go straight to the formula. So let's dissect this one more time. A of t is the amount at time t years. 100, remember, was the initial amount. For anything that's exponentially growing or decaying, you have to have a seeding amount. You have to have a starting value. And I told you yesterday we started with $100. The 1.3 was very interesting. 1.3 as a percentage is 130%, which, because we were gaining 30% a year, we were getting 100% of what we had previously plus an additional 30%. So 130% as a decimal is 1.3. And then, of course, t was the time in years. So 130% each year. All right, so in example 2, very similar, except now instead of gaining 30%, we're going to lose 30%. We start with $100. We're going to lose 30% every year. We want to write a model to predict now the amount at t years. So if we did this by pattern recognition, the only difference would be, like on t equals 1, it would be everything we had before minus 30% of that value. T equals 2, it would be the previous amount minus 30% of that amount. So we're going to have minus signs there instead of plus signs. So let's see if we can go straight to it. The amount now at any given time t is going to still be the 100 that we started with, but if we're losing 30%, instead of 100% plus 30%, like we did on example 1, this one's going to be 100% minus 30%, which leaves us what? 70%. And what's 70% as a decimal? 0.7. There you go. And because it's every year, it'll be to the tth power. That's it. That is your model. So that's another way to think about it. If you're losing 30% every year, you're actually retaining 70% each year. And your exponential models always tell you what amount you're going to have, not what amount you lost. So in number 1, we had 130% every single year from the previous year, and here we have 70% of what we had the previous year. And of course, because 0.7 is a base less than 1, what type of function is this? Growth or decay? It's a decay function. So our money is decaying. Not real good if we're trying to earn money. We're losing quite a bit here. All right, so that's an important idea, which now we're going to summarize right here. For the exponential growth and decay models, to model a real-life situation, if A is some amount, and if it's changing at a constant percentage rate R, okay, like this one was increasing 30%, this one was decreasing 30%, each time period t, then you could come up with this equation. A of t, again, is the amount at times t, equals A sub 0. What is A subscript 0? The starting value. Yeah, the subscript corresponds with t equals 0. So this is the initial amount. The initial amount corresponding with t equals 0. We'll say at t equals 0. And notice on the inside, it's 1 plus r to the tth power. Big R is your percentage rate, and little r is going to be the decimal version. It's the decimal version of big R. If that number is greater than 0, it's going to be growth. That means we're adding something like 30%. If R is less than 0, it's going to become decay, and it turns into 1 minus R, essentially, like on example 2. All right, so you can think of little r as kind of being a vector, and big R as well. Okay, so here's some terminology. They're closely related, but they are different, and we're going to practice using it. If A of t is exponential growth, like at example 1, we call big R the growth rate. The growth rate is going to be the percentage rate. All right, so in example 1, that was 30% gaining. The growth rate was 30%. In example 2, the decay rate was 30%. So that's the growth rate. 1 plus R, which is essentially the base, that's called the growth factor. Not the percentage rate, not the rate, but the growth factor. If it's decay, then big R is the decay percentage rate, and 1 minus R is called the decay factor. So again, 1 plus R and 1 minus R, that ends up being the base of your equation. So let's come back up here and see what it would look like on example 2. The decay rate was equal to 30%. The decay factor was equal to what? 0.7. Good. And the reason we call it a factor is because exactly how exponents work. If you increase t by integer amounts, it tells you how many factors of the 0.7 you have, right? When t is 1, you have 1 factor of 0.7. When t is 2, you have 2 factors of 0.7. You're multiplying by 0.7 the factor, however many times the t is. That's just the definition of exponential. But the rate is the difference from 100%. Okay, if you want to add that here, the growth and decay rate, that's going to be the difference from 100%. You can't just take the base and turn it into a percentage. In other words, up here, we're not going to call the decay rate 70%. We're going to call the decay rate 30%, because this is 70% retaining, 100 minus 70 is 30. We're losing 30%. Just like up here on number 1. The growth factor is 1.3, but we do not call the growth rate 130%. We just call it 30%. So the percentage rate is always difference from 100%. We're going to practice it right now in example 3. Determine the growth and decay rates and the growth and decay factors for each of the following. So A of t equals 6 times 1.046. The 6 in the front is just the starting value. So 1.046 is your base, and because it's greater than 1, this is going to be what? Growth or decay? Growth. So we want to figure out what the growth factor is, and we also want to figure out what the growth rate is as a percentage. So what is the growth factor? Yeah, 1.046. The growth factor or the decay factor, it's always just the base of the exponential equation, right? Because again, that's how exponents work. What is the growth rate? Is it 104%? Just 4.6. Yeah. If you want to convert the base to a percentage, that is 104.6%. All you have to do is subtract 100% from it, and you get 4.6%. Okay? So something that grows by 4.6% each year is the same as increasing by a factor of 1.046 per year. So anything that increases by a constant percentage rate or by a constant factor at regular intervals is going to be exponential. All right, so far so good? Not that bad? Letter B. Let's do this one together. The 3 is the starting value. The base is 0.14159. That's less than 1, so this function is going to be what? Growth or decay? Decay. So we want to list the decay factor, and we want to list the decay rate, percentage rate. Well, the factor is easy if you have the equation. What's the decay factor? 0.14159. Good. Now, for the decay rate, you probably need a calculator for this one. It's going to be the difference of the factor as a percentage from 100. So 100% minus 14.159%. if you do that, let's see, I still have it from earlier. No, I don't. 100. You could also do old school subtraction, stack subtraction, and borrow. 85.841. 41%. So that's the decay rate. We're losing about 86% per cycle, which means we're retaining about 14%. And the exponential model always tells you how much you currently have, not how much you currently lost. All right? Okay, do this one on your own. List the growth or decay factor and the growth or decay rate. This one is sometimes eye-opening to some people. I put growth down. I hope that wasn't revealing too much. The base is 2. It's greater than 1, so it is a growth function. What's the growth factor? 2. It's just the base, right. So this would be something that doubles every cycle, like cell division, right? Times 2, times 2, times 2, times 2. That's the growth factor. So something that increases by a factor of 2 is increasing by what percentage? 100%. Good. If you turn the factor into a percentage, you get 200%. Because it's bigger than 100, you subtract 100% from it, and you get 100%. That's news sometimes to some people. If something doubles, it increases by 100%. Some people think if it doubles, it increases by 200%. That wouldn't be the case. If something triples, it increases by what percent? 200%. Right. If something quadruples, it increases by 300%, so on and so forth. The percent rate that it grows or decays is always the difference of the factor as a percentage from 100. Okay? Sweet. So we got that down. I'll be asking you for both of them on tests and quizzes, so make sure you know the difference betwixt the two. All right, let's go ahead and try it out. Compare and contrast the Tale of Two Cities, right? The non-Dickens version. The Tale of Two Cities. Sunny San Jose, California, and Detroit, Michigan. Okay. So populations grow exponentially. So we can use exponential models to describe the populations. So the model that we have here for sunny San Jose was a model that was created shortly after the 90s, okay? T equals 0 is going to correspond to 1990. So that means that this data was collected on the population of San Jose probably in 1990, 1992, 1994, 1996, whatever, every 2 years, maybe every 1 year, or maybe the grand census every 10 years. But once you collect those data points, these actual data points, you could plug them into your calculator even and come up with a regression equation for it. And once you have the regression equation, you can use that equation to either predict within the data, like if I took the data in 1990 and in 1992, I can use the equation that I get to predict what the population was in 1991. Whenever you predict within the data, let's go ahead and write that down. Whenever you predict within the data, it's called, anyone know? Close. Interpolation. I heard. That's kind of the P sound. Interpolation. If you are using to predict outside the data, so let's say my last data point was in 2010. I took data from 1990 to 2010. If I then use that model to predict in 2011 or 2017, predicting outside the data is called extrapolation, or extrapolation is the where you put the accent. Extrapolation. Extrapolation. Now, there's always more risk in which one of these, do you think? Extrapolation. There's always more risk in extrapolation. Within the data, you're a little bit safer because you have data points on both sides. But if you're using your model to extrapolate, which is usually what we do, right now we have city planners trying to predict what's going to happen with Comal County in the next 10 years. And they came up with a model, and they're using it to predict so that they can plan how to have infrastructure in place for these millions of people that they're predicting are going to live in Comal County. Okay? There's risk, though, because if you extrapolate too far outside the data, you get unreasonable numbers. So extrapolation is good when you have a lot of data points and you're predicting for short times outside the data, not too far outside the data. But anyway, let's look at this model from sunny San Jose. The model was already given to us, so we don't have to worry about how it was collected. But t equals 0 corresponds to 1990. So according to the model, how many people lived in sunny San Jose in 1990? 782,248, right? That's the initial value, so that corresponds to 1990. Also, according to the model, because the base is 1.0136, was the population of San Jose growing or decaying? It was growing, right. San Jose was a city that was attracting a lot of people. It had a population boom. And if you've ever been to San Jose, the good parts of the city, you might know why. It's pretty there. So let's go ahead and first of all list the growth factor and the growth rate. All right, what is the growth factor? Yeah, 1.0136. That's easy. That's, if you have the equation, it's just the base. The growth rate is going to be the difference of that number as a percentage from 100, which for a problem like this is pretty easy to get without a calculator, right? What would be the growth rate? 1.36%. Good. Because if you put that as a percentage, you move the decimal 2 to the right, you get 101.36%. Subtract 100 from it, and you get 1.36. So that means every year, according to the model, the population was increasing by 1.36%, which is pretty good growth. Okay? Let's go ahead and see how accurate the model is. If we go to our internet resources, right, let's see if we can find a current population for San Jose. Current population of San Jose, California. All right, so there's an estimate right there. In 2016, the population of San Jose, that's probably a predicted, it says from the U.S. Census Bureau, I guess it's hard to get better than that, 1,025,000 people, approximately, all right? In 2016, we'll say that this is the actual number, even though that's probably just a safe estimate. I don't know if they go down and count to the nearest person. But let's see if the model, what the model would predict, okay? According to the model, then, I would have to plug in a what to get 2016? 26? Yeah, if t equals 0 corresponds to 1990, 2016 was 26 years after that. So P of 26. Well, now we'll go to the calculator. Since we're only doing one calculation, I'm not going to put it into Y1 or anything like that. I'll just go straight to the home screen and type it in. So 782,248 times 1.0136 raised to the 26th power. And the model predicts that there was 1,111,414. Look at that, 0.632 people. These people are forming as we speak. Look at that. All right, so did the model do a decent job of predicting? Yeah, pretty decent, right? Not bad. Not bad at all. It's predicting that San Jose was growing a little bit faster than what actually happened. And so I don't know when the last data points were. Maybe this data point was only from 1990 to 2000. In that case, we're projecting 17 years outside the data. That's not really the best practice, but there you have it. It's pretty darn close, all right? So if you wanted to get a better approximation, you would collect more data, or you would predict less distance outside the data. But San Jose is still growing to this day. And now the tale of two cities, Detroit, Michigan, Motor City, America, right? What's happened to Detroit in the last decade or so? Population has gone down. When the automotive industry busted before the federal government bailed it out, a lot of people in Detroit lost their jobs and they moved elsewhere. And there's entire subdivisions in Detroit that are like ghost towns, all right? So this model was corresponding to 1980 with t equals 0. So it's an even older model. But according to the model in 1980, what was the thriving population of Detroit, Michigan? 1,203,368 people, okay, in Detroit, Michigan. Now, according to this model, even back in 1980, what was happening to the population? Increasing or decreasing? Decreasing. So for whatever reason, this was well before the auto industry fell. Let's go ahead and list then the not growth factor, but decay factor. So when we say the population is decaying, we don't mean like Walking Dead decaying. The population is not literally decaying into zombies. It's just the population is decreasing. So the decay factor is 0.9858. Very good, 0.9858. So we're retaining only 98.58% of the population every year, which means the decay percentage rate, or the decay rate, is 100 minus 98. 1.42, thank you. 1.42%. So if you compare that with San Jose, notice, according to the model, people were leaving Detroit at a faster rate than they were getting to San Jose. So if you had the theory, the very shallow theory, that everybody who left Michigan went to San Jose, it's probably not true, right? Maybe one of them went to San Jose, but not all of them. All right, so let's see how well this model predicts in modern times. Let's see what the current population is of Detroit, Michigan. Oof. In 2016, the data says there were 672,795 souls. Now, Detroit in the last couple of years has kind of started moving up again, but let's see how well the model predicts. According to the model, 1980 was t equals 0, so 2016 would be 36 years later. So let's just type that into the calculator one time, so we'll just type it in. 1,203,368 times 0.9858 raised to the 36th power. The model says that there's going to be 110.7085 people. So if you compare the two numbers, what actually happened was a little more dire than what the model even predicted, right? People left Detroit at a greater rate than what the model would have predicted. So anyway, it's pretty close though. Yeah, it's kind of impressive. And so this is what city planners do. They use current information to create mathematical models to try and predict so that in the future they'll have infrastructure. So maybe the loop out here that's about to get going, making it a 5-lane with 4 lanes with a turn lane in the middle, maybe we're kind of overdue for that, right? Maybe that should have happened already a few years ago. You don't want to have to be reacting to population booms. You'd like to plan ahead and be ready for them when they come. So anyway, there you go. There's an example of growth and decay, and we kind of practice our new terminology. Comal County, I believe, is one of the fastest growing counties in the United States. currently right now. I did hear some number on the radio the other morning of about 1 million people. I forgot by when. It might have been 2020. That's only 3 short years away. But Comal County itself is growing pretty rapidly. All right, another application of exponential growth and decay is when you're talking about bacteria. Ooh, bacteria. It's the only culture some people have. Here we have a small culture of bacteria. 10 of them, only 10 of them. 10 hoodlums, essentially, getting together in a petri dish. All right? Suppose that the culture of bacteria doubles every hour, and that's pretty reasonable. After how many hours will the number of bacteria reach? 500,000, half of 1,000,000 bacteria. Well, there's 2 ways to do that. On your calculator, if you start with 10, multiply it by 2, okay? So when t equals 1 hour later, you got 20. Hit times 2 again. So after 2 hours, you have 40. Now on your calculator, if you do something twice in a row, it remembers what you're doing. So if you just keep hitting enter, 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 you can actually see what's happening to the population. And it's doubling every cycle, and boom, right there. I didn't have to click very long before my population went from 327,000 to 655,000. So 500,000 would be somewhere in between there, right? So if you counted how many times I hit enter, you can kind of get a ballpark idea. But we want to get better than a ballpark, right? We want to get down to the nearest 3 decimals. Exactly when will the bacteria reach 500,000? So we need to write a little mathematical model. Let's give it a name for the amount of bacteria at time t. You want to use A for amount, B for bacteria, C for culture, F for fun? B for bacteria. Okay, so the number of bacteria B after t hours is going to equal, kind of like we did in example 1 and 2. What was the initial amount? 10, so that's going to be our A value. What is the growth factor? 2. It's doubling every hour. So the growth factor is 2, and because it's every single hour, you could just put t. So notice when t is 1, it's going to get 1 factor of doubling. When t is 2, it's 2 factors of doubling, so on and so forth. That's a pretty little model. Easy to write as well. Now if I want to know when it reaches 500,000, I plug in 500,000 for what? T or B of T? B of T. So 500,000 is going to equal 10 times 2 to the tth power. And in the next section, once we learn how to work with logs, we're going to be able to solve that for T and get an exact answer. But right now, we're not going to do that. We're going to solve this the way we did for the logistic equation. We're going to solve it not giraphically, but graphically. Giraphically, yeah. That's like doing it with a long neck. 500,000. I'm going to put that in Y1. What the heck? In Y2, I'll put the other side. 10 times 2 to the x power. Now, if you hit zoom 6, that's being lazy. We're going to pick our own window. A good x-min would be 0 or -1. I like -1. I like to see the y-axis. But we're starting at t equals 0. Now, this is kind of where we don't know what to set for our maximum time. But I think 24 hours is a good time to start with, right? Let's let these little rascals go for a day, 24 hours. We'll turn our x scale to 0. And now for the y-min, again, 0 is good. We know we're starting with 10, so it never gets below 10. I'm going to put -1 just because I like to see the x-axis. Now for the logistic, we always took a cue from what the numerator was. In this case, we want to know when it equals 500,000, so I'm going to put my y-max a little bit above that, 600,000. That leaves us a little room at the top of the graph for the graph's writing. And then, of course, turn your y-scale to 0. So you don't get 600,001 tick marks. Now you hit graph, and you should see the 2 intersecting. So notice it starts off growing very, very slowly. But the time value of bacteria and the time value of money as well, if you can wait a little bit longer, then towards the end of the cycle, A doubling factor is going to get you a lot more than when it doubles down here early. So when you start getting money in your profession after college, sock that money away in investments early and keep doing it. By the time you retire, at the end, you'll have exponential growth working its full powerful effects. All right. So for us, second trace number what? 5. Only 2 curves, only 1 point of intersection. So enter, enter, enter. And we end up with T equals 15.609 or 610 hours if you round. I like to truncate. So there you go. It took a little over 15 and a half hours for it to become $500,000. What's going to happen to that culture in the next hour? So after 16.609 hours, it's going to double and become $1 million. Then at hour 17.6, it's going to be $2 million. At hour 18.6, it's going to be $4 million. That is fast, all right? So at the first sign of some kind of bacterial infection, you want to go get antibiotics, okay? Don't wait. Don't wait for it to go away on its own. That's what landed me in the hospital last December for 18 days. Yep. I had a chest infection, and they gave me antibiotics, but they weren't strong enough, and the bacteria took over, and I ended up with what they call an empyema, which is basically a bacteria party in your body. And I was in ICU. They had to go through my rib and pressure wash it all out, and I was on strong IVs for 18 days. That's how I spent my Christmas break. Okay, and I knew about exponential growth, so they just assigned the wrong bacterial disinfectant or antibacteria.
Power wash your inside?
Something like that. I think they hired Mr. Wenzel in the operating room to come in and spray between my ribs, clean out my chest cavity. So anyway, bacteria grow exponentially. Bad if it's bad bacteria. Not all bacteria is bad, right? Bacteria in your stomach is good, helps digest food. But anyway, if your money starts growing like this, just let it go. Just say, cool, man. All right, I'm going to watch. If it's bacteria, though, and you're getting sick, get help. Get professional help. All right, we're going to stop right there. All right, we're going to stop with example 5. You have a little bit of time to use the calculator then, if you want, to try and do some of your worksheet problems with the calculator.